When exploring new areas, robotic systems generally exclusively plan and execute controls over geometry that has been directly measured. Here, a spot robot competing in the DARPA Subterranean Challenge experiences an influx of new information when it moves to see the open room on its right. After extensive replanning given this new information, it eventually competes the optimal path to continue its exploration down the hallway. To address this inference problem, in March of 2024, we created a diffusion-based occupancy synthesis framework, SceneSense. SceneSense seeks to generate complete realistic occupancy maps from partial observation using a method we call occupancy inpainting. Occupancy inpainting enforces that observed occupancy is maintained while unknown space is allowed to be predicted as occupied or not. In these videos, we show examples of SceneSense predictions made in a simulated environment where predictions are made around the robot. While this pioneering work shows the promise of SceneSense as a method for occupancy predictions, there were some limitations to a direct translation to a real-world platform. In this work, we provide key modifications to the existing SceneSense framework to allow for successful onboard deployment. In particular, we 1. Update our method for map merging by updating the existing Octomap map merging formula. 2. Make key modifications to the SceneSense inference framework to allow for diffusions anywhere in the map, as well as a 73% reduction in inference time. And 3, implement a graph-based planner, GB planner, for map frontier evaluation and selection of points of interest for occupancy prediction. We provide evaluations of all the proposed methods in the 2 test environments shown here. Here, we show our robot-centric occupancy predictions in real time onboard our Spot robot in a new test environment. In this configuration, SceneSense is generating occupancy predictions around the robot at 2 Hz. Then, the predictions are merged into the running occupancy map using our probabilistic update rule. As you can see, the predictions enhance the running occupancy map, filling holes in occluded geometry in the scene. Next, we show an example of our frontier-centric predictions in the same environment. To start, we run robot-centric diffusion as before to fill in unobserved geometry around the robot. After some traversal, we initialize the graph to build. Then, we identify points of interest for occupancy prediction, which we will circle in black. In this case, 3 points are identified, 2 in front of the robot and 1 behind. Once the points are identified, SceneSense begins predicting occupancy at range. 5 predictions are made at each point and merged into the running occupancy map as they are produced. The resulting map is shown here, with extended geometry that could be used for robotic exploration or navigation tasks such as planning or path selection.